This, and the other learning resources in this course have been made possible by funding from the European Commission's Erasmus Plus program.
Voila. So, from today on, we will work on digital tools for heritage management part 3, laser scanning. And if you click here, you will again find various chapters. So let me open the first one. This session is actually, remove highlights, show topic. For the participants that are totally new to this specialist course, this first introduction will give you an overview of why we are working on digital tools for heritage management. So what is the relevance of this summer school and of the various topics for heritage documentation and heritage management in general. So in my previous course on photogrammetry and image-based 3D modeling, I already covered these presentations, but if you are new to the group and you want to have more information about these presentations, please feel free to contact me via email or via the WhatsApp group. For all the participants, I would like to invite you to have a look on the first exercise, or the first task. It's actually identical to the one that you have been working on on the part of photogrammetry, but in this case, I would like to ask you to do some literature research on the use of laser scanning for cultural heritage, so archaeology, heritage management, and so forth and so forth. So yeah, of course, I assume that you don't have a laser scanner at your office, or your institute, or maybe your institute has a laser scanner. That's a very big advantage. You can acquire your own data. But if you don't have it, you can just pretend to have one and imagine yourself, okay, I want to make a 3D model of this artifact or this artifact. How would I deal with that? And on the fly, I will also give you some references to documentation, specifications, and some literature that might be useful for you. Given the fact that you might or you might not have a laser scanner, or you might not be able to work on your own laser scanning point clouds, we will pretend that the data that you acquired in the previous session that is your own data, and that we acquired it using laser scanner. So you had your photos. The photos were converted to a 3D model, and from the moment that you have your dense point clouds, you will make an LAS file using the export functionality in Metashape, and then you can pretend these data to be from a laser scanner, and all the exercises can be done using these data. If you're totally new to the group, I will make sure that you will have an additional laser scan point cloud. Coincidentally, yesterday I went on the field, so I have a brand new point cloud that you can work on of my municipality here in Belgium. Today we will be talking about the fundamentals of laser scanning, so it will be a very theoretical discussion on what is laser scanning, what is the technique behind it, what are the different types of laser scanner that are applied in the field of heritage management. So we will discuss about that. And I would also like to mention that for this presentation, there are multiple videos available also on the Moodle platform that you can access by just clicking on the yellow box. And then here you can find the various chapters. Hello? Normally you will find the various chapters here in this box, but apparently my internet does not allow me to. It was, but it's just a little bit too fast. Tomorrow we will be talking about data management. So if you acquire the data, how can you work with these data? How to deal with these huge point clouds that you can obtain using laser scanning. So that's the topic for tomorrow. Also a more theoretical discussion that we will have, and also accompanied with some videos that are made for the preparation of this summer school. Then on Sunday we have a free day, and on Monday we will have a guest lecture from an Italian friend and an Italian colleague working for Leica. And he will give a presentation about applications of laser scanning with a special focus on cultural heritage management. So he will show you some applications of laser scanning, in this case, mainly in Italy. Very interesting. And he also prepared a video and some slides that he will discuss with you. On Tuesday and the days to follow, we will work with data ourselves. So also on the platform, on the website geo.horitage/cs. For the people that are totally new to the group, I will add it to the chat functionality, this URL. Chat. Hello, where's the chat? Yeah, voila, there we are. And I will send the URL to you, voila. And under this link, you can find all the data sets that we will use for the laser scanning course. Some of the data sets are quite massive. So if you experience problems downloading these data or processing these data, please let me know as soon as possible that you're not too much delayed. So if you really see that your system is slowing down and that the point clouds are too difficult to process, let me know and I will make sure that you will have a reduced point cloud, but that you can still work on the different exercises. So you will find the different data sets here. Let me go back to the platform. So in this practical sessions, we will talk about Cloud Compare, an open source program for point cloud processing. Obviously, for your own projects, you will work with your photogrammetry-based point clouds, but conceptually, a point cloud is a point cloud. So we will just work on that in Cloud Compare. I will show you some of the basic functionalities. You can experiment with that. I also prepared a task for you to get more familiar with it. And then using Cloud Compare, we will focus a little bit more on point cloud registration. So if you have multiple scans taken from your environment, how to make these point clouds into one massive, spatially coherent, unified point cloud. So we will have a discussion about that, and I also prepared some tasks for you. With a laser scanner, you will get a lot of noisy data. I'll show you some of the noisy data after this introduction. But there are some techniques to filter these data. So you will learn how to do this filtering yourself, what techniques to be used, both automatic filters and manual filters. And then some point cloud deliverables. So that's actually the same as the thing that we have discussed while talking about photogrammetry. So if you have a point cloud, how can you extract useful deliverables from these data? And then not only digital elevation models, but also profiles and cross sections, digitized plans, etc. And then the last part is also quite similar to the one that we discussed the day before yesterday. That's about publishing data. In this case, we will also use a local server, and this server will be used for online pseudo-online server-based point cloud visualization. So if I go back to my website, I have some interesting examples of that. Let me, for example, here to Navplio. So this is actually the page in front of heritage.cs. And if you click here on this image, you will get access to a JavaScript-based point cloud visualization tool, and you will implement something similar as this, where you can actually load point clouds into a viewer, and that is incrementally loading points that are in your field of view. So you will use something like that, or you will implement something like that in the last exercise, the last day. So that's a little bit about the organization of this part of the specialist course. Also, I would like to mention that for the general task for the entire summer school, I would like to stress that the tasks are implemented or prepared for you to get familiar with the topics, to get some kind of a Fingerspitzengefühl, or some to get everything in your fingers. The practical parts of the summer school. We will not have a qualitative evaluation on these tasks. So if you are really experimenting and you're uploading erroneous data or erroneous reports, don't bother too much about it, because I will not give you an F or a negative quotation for that. It's just for practicing. It's just to make yourself familiar with it. And wherever possible, I would like to give feedback on it. I also received from one of you some emails with requests for feedback, and I really do my best to speed up that process and to give answers as soon as possible. For example, one of you participants sent me an email about local referencing of a 3D model, and in order to demonstrate that, so at the end of my presentation, I will demonstrate that that principle using a box. So I have a box here. Borrowed from one of my kids. So a Winnie the Pooh box. I made a 3D model of the front of this box, and I will show you how to make this a reference model using a simple ruler. So we will do that. We will do that together, but of course after the presentation on laser scanning. The general task. So all the separated tasks that are presented during the workshop are for exercising. I will try to give feedback on these exercises. There is, however, a general task for the entire summer school that will allow you to get a certificate of attendance, or a certificate of participation. I don't know the correct vocabulary for that. And that exercise is in finalization phase of the preparation, and it will be something like a report, a full report on, okay, you have an object somewhere, how would you make a 3D model of it? And you will make some kind of a research paper, or a paper on how to make a 3D model, show your results, and discuss a little bit about the quality, about the data acquisition parameters. But I will communicate that as soon as the exercise is ready. I don't know so far if you have any questions. In general, also for the people that are totally new, if you have any questions, feel free to interrupt me, and I will try to answer the questions as soon as possible, assuming that my chat thing pops up. Apparently there's a problem with downloading the files. Let me see what the problem could be. It seems to work on my computer. So if you have problems, maybe it's because of the fact that you used a comma in the URL, but I am able to download the data. And I think all the references are also set correctly. So if you experience problems with the data, so now we're talking about laser scanning, please feel free to contact me. And let me know. But I don't see the source of the problem that is just mentioned here. But Dionysos just mentioned that there was a problem with downloading it, but in the URL that is used, there is a comma behind the slash, so that may be the problem.
Can you try to download the session 5 demo data?
Aha. Okay, you got me here.
Okay. I don't know why.
Thank you.
You're welcome.
Let me see. 05 demo data. Ah, the demo data was just not uploaded. I will I will upload the data. Thank you very much for mentioning this. Let me do that instantly. By the way, this should all be clipped from the recording, of course, the demo data. Voila, it's being uploaded now. So I will let you know as soon as it's ready. But thank you for your remark. So let's go back. I hope the internet connection stays stable. Are there any more questions so far? Then let's talk about laser scanning. So today I will give you an introduction about laser scanning in general, just a brief overview of the technique itself. How does it work? How do you derive distance measurements from a laser? The things that I'm going to discuss with you about laser distance measurements is actually exactly the same as the technique that you will find using when using a total station, for example. I don't know if you are familiar with a total station, but a laser scanner, if you put it very naively, a laser scanner is just an automated total station, but instead of pointing in certain directions manually using your visual eye, you set an angular increment and it will automatically measure a lot of points. So we will discuss about these basics and the way that distances are derived. I will also give you a system classification. So most of the time you will be working with static laser scanning. So that's actually the thing that I also presented to you when I sent the messages in the WhatsApp group. And if you're not yet a member of the WhatsApp group, I definitely would recommend you to become a member of the group. So yesterday I was actually using a laser scanner for the acquisition of a lot of points of an cultural heritage site here in my village. I can show you some of the pictures, I think. So if I go not to this folder, but let me go to this folder and see if I can, yeah, voila. So this was the laser scanner that I've been using yesterday. Just some impression video of impression photos, the laser scanner, and actually the artifact that I was asked to model was this building on the background. And then by using a laser scanner, you can obtain data like this. So this is actually what you see here is actually a preliminary result of the data that I acquired yesterday. These are only 3 of the 5 scans that have been generated. And each and every scan, in this case, contains either almost 7.5 million points, or as you can see here, 30 million points. So actually the number of points can be massive, can be extremely large. And it's quite an interesting challenge to see how you can work with these kinds of data. And that's one of the topics that we will definitely discuss during this specialist course. There's another question. I will check afterwards. Yeah. Demo 7, let me write it down. Upload. So statical laser scanning is the technique that I applied yesterday. We will also talk a little bit about mobile laser scanning. So the situation where you have a laser scanner and a motion sensor and a platform and some other hardware. You put it on a van and then you can just drive through your site, over your site, and you can acquire your data in a kinematic fashion. And another way of acquiring kinematic data is, of course, airborne laser scan data. I know that especially in the United States and in many European countries, you can have free access to airborne laser scan data. So that's actually the situation where the vendor of the data has put a laser scanner in an airplane. The area has been flown over by the airplane or a helicopter, and you can have laser scan point clouds of your area of interest. And then afterwards, I would like to close this presentation with a sneak preview on some deliverables and some closing remarks on why you would use a laser scanner. So laser scanning, what is laser scanning? If you go into the literature, you can actually find a lot of abbreviations for it. You will see in a few slides that the main principle or the main technique behind laser scanning is light amplification by simulated emission of radiation. And you all know that that long sentence as laser. So we will use laser light to acquire our data, and then using laser, actually laser scanning and laser. The combination of those is then laser detection and ranging. So that's an abbreviation that you will frequently find in literature, laser detection and ranging, or light detection and ranging. LiDAR is also quite frequently. Coincidentally, last week, one of my colleagues was talking about laser sensing. So laser sensing is also one of the things that we can add here for the acronyms. Well, all these things are actually based on a technique to sample or to digitize a 3D surface by means of an active laser technology. So that means that we are going to acquire massive point clouds. So massive point clouds, meaning that we will acquire the geometry of a surface in terms of XYZ coordinates. So you will see that the laser scanner will actually, if you go into the laser scanner itself, it will record Cartesian coordinates, so distances and an horizontal and a vertical angle. And these are then converted on the fly to Cartesian coordinates. Possibly we can also obtain an intensity value. I will explain that a little bit later, how that works. We are emitting a signal, we have an echo of that signal, and there's a loss of signal caused by mainly caused by the surface that that will have this echo, and the difference is then used as an intensity value, and even combinations of geometry, intensity, and if you have a camera attached to your laser scanner, you can also have colored XYZ coordinates, colored point clouds. Depending on the distance, you can obtain very, very high resolutions. So in terms of, for example, if I speak to the Flemish case, if you're talking about the Flemish region, the entire Flemish region has been covered by airborne laser scanning with a resolution of 16 points, 8 to 16 points per square meter. So the entire Flemish region has been covered with that density. But if you use laser scanning in terrestrial applications, you can actually go to hundreds or even thousands of points per square centimeter. So these ranges are the working range that we are talking about. And like I already said, if you have a laser scanner and the possibility to integrate your laser scanner with additional hardware, like a camera, like a GNSS or a motion sensor, an IMU, inertial measurement unit, you can use your scanner as a kinematic platform, a combination of the motion sensor and the GNSS, the satellite system of satellite navigation. And with the camera, you can obtain true color point clouds, like the one that I just showed you here. This is also acquired by a scanner, and the scanner includes an RGB camera. So that's merging the camera images and the geometry from the scanner will end up with, or will result in a true color point cloud. So yeah, these are the things that we are talking about in most of the cases. And if you look in literature where, for example, I'm the author of those papers, I frequently use LiDAR as an abbreviation for laser scanning. So LiDAR, light detection and ranging, which actually means all the techniques in which light is used to derive the distance between a sensor and the object or a surface. So we have a sensor, we have an object, there's a certain distance in between, and we will use light to extract this surface. And not necessarily visible light, but in most cases we will use infrared or near infrared light. But I will also discuss that in one of the coming slides. If we have a large number of these distances combined with angular measurements, we will actually have a very dense point cloud within a very limited time frame. So the scanner that I've been using, it's a Leica C10 laser scanner. These 25 million points are obtained in half an hour. So what I did, I set up my laser scanner, I set my resolution, I set my field of view, and in my case, I just measured everything. And the result of that half an hour later is a very dense point cloud, 30 million points of my entire sphere. And actually, if you look into the more recent instruments, the more recent laser scanners, you will find laser scanners that are able to obtain 500,000 to 1 million or even 2 million points per second. So the measurement rate can be extremely high. The general properties of laser scanning, I've summed them here, is that we're working with an optical system. So in that case, it's actually very similar to the things that we've seen in photogrammetry. We're using optical systems. But in contrast with photogrammetry, we used environmental light. So we need the sun, we need an external light source to illuminate our object. And this external light source and the reflection from our object will allow us to make a photo. In this case, we will work with an active system. So it means that if we have a scanner, the scanner actually contains a system that will emit a certain amount of energy, a signal, and that signal is emitted, and the reflectance of that signal will result or will be the basis of our distance measurement. This reflection is also very important. It is reflection based. And the properties of this reflection, the properties of this echo will also allow us to extract additional information from our point cloud. And then, as with photogrammetry, we are also working in a contact-free environment. So we don't need to touch the system. We can actually mount our laser scanner on a platform, an airborne platform, a kinematic platform, just a driving platform, or set it on a tripod. And then in that case, we don't need direct physical access to the object, so it's contact-free. The different types of laser scanning for very close range applications, we will work with triangulation-based laser scanning. So in that case, we have the projection of points, lines, or patterns, so structured light scanners, for example. And this light is projected on the object that we want to measure, that we want to model in 3D. And the reflection of that pattern will actually generate a 3D reconstruction of that surface. A couple of years ago, I did an experiment with that. I found a tutorial online how to make your own laser scanner. And actually the only thing you needed was a laser pointer, the foot of a glass of wine or a wine glass. And by emitting that and having a certain baseline system, you were actually able to extract some 3D information out of it. The accuracy of that system was not very good. Obviously, it was not very good because I was not working in a calibrated environment. But still, the idea of these laser scanners was quite interesting to get a better understanding of how it works. And if you want, I can also look for this tutorial and share it with you. In most of the applications that you will be using in heritage documentation, you will use time-of-flight scanners. And time-of-flight scanners, there are two types of time-of-flight scanners. You have the pulse time-of-flight, we'll discuss that later, and a phase shift scanner. So these are now we are talking about time of flight cameras, 3D cameras, range cameras. So for example, if you go to a construction shop and you look for a distance ranger from Bosch or from the Wald or anything, these small devices with a pointer in it, when you press the measure button, what's actually happening is you send the signal, you have an echo of the signal, and based on that you will be able to calculate the distance quite accurately. These time of flight scanners and phase shift scanners are also implemented in most terrestrial applications, in terrestrial laser scanning and terrestrial kinematic applications like mobile mapping, but also airborne laser scanning makes use of these time of flight scanners. If we talk about laser scanning using an airborne platform, most of the time we talk about airborne laser scanning or airborne LiDAR, as you will also find it in literature. And a frequently used abbreviation for that is ALS. So if you look for airborne data, ALS is the abbreviation to look for. And light has this very annoying or very useful, depends on how you put it, a characteristic of being heavily absorbed by water, especially when you use near infrared or colors in the spectrum. And in order to use airborne laser scan data also for bathymetric applications, you will not only use a red signal or an near-infrared signal or an infrared signal, but also a green signal. And by having these dual frequency or dual wavelength laser scanners, you're also able to penetrate a water column and even have the surface under your water level. And these techniques, or this technique, is called airborne laser bathymetry. Where I'm from Netherlands, I live in Belgium. We have the North Sea as our neighboring sea. And for the North Sea, I would definitely not implement laser bathymetry because of turbidity. But if you're living in the Mediterranean area, or if you're living in the Baltic Sea, for example, most of the papers or the first papers were written about applications in the Baltic Sea where the water is very clear. These are very interesting sites to use laser bathymetry. And also radar is a technique that is frequently used. For spaceborne applications, you will also find a way of implementing laser scanning. But in that case, it's using a different technique with other wavelengths and other frequencies. But there is an option to use spaceborne laser scanning. I think that SRTM data is derived from radar. There is a mission currently running that uses laser scanning for the extraction of digital terrain models on a worldwide scale, but of course with a very limited resolution. So for example, the implementation of radar for SRTM, so that's actually the data that you can download for free, the global digital terrain model, that is extracted from radar, also an active technique, and that has a resolution of 30 meters out of my head, 30-meter resolution, as good as worldwide, except the poles are not included in that data set. So yeah, the biggest advantage of laser scanning is that we can make very complex 3D scenes. So we have the ability to make very complex representations of complex geometries. And with photogrammetry, that's also possible, but definitely more difficult, especially when you're working in indoor environments. In that case, it's very difficult to implement photogrammetry to make a full coverage of your indoor space. Laser scanning from that perspective is more feasible, more suitable to make indoor geometries, indoor representations of your environment. And another very important advantage of laser scanning is that the fact that since we are working with an active system, so we are generating our own signal and we are emitting our own signal to our environment, we record the echo. It also means that we don't have to deal with the big disadvantages of photogrammetry being the lack of texture in our object. Maybe if you have experiment with photogrammetry and you've taken a very flat surface or a very glossy surface or a surface that just doesn't have any texture in it. So for example, a white box or a box without any contrast in it. In that case, it's extremely difficult or maybe even impossible to use photogrammetry. But if you want to make a 3D model of that object, laser scanning is a very suitable way of having a geometrical representation. Also, the lack of environmental light. So even in dark rooms, we will be able to use laser scanning because of this active recording system. And when I started my PhD in 2009, one of the first applications I was working on was the measurement of tunnels, of railway tunnels under the national airport, international airport in Brussels and the harbor of Antwerp. These were very narrow, very dark environments where we had to measure cross sections of newly built tunnels segments. And in that case, it was very suitable to use laser scanner. So we just put our laser scanner, we make our scan, and we could move again. Whereas with the implementation of photogrammetry, in that case, we need environmental light. We need to place lights around our object or inside our object, and it would be much harder to get an appropriate result. If you go into literature, and especially in literature that goes back to, let's say, 10 to 15 years, it is also said that laser scanning is much more accurate compared to photogrammetry. Currently, I wouldn't say that anymore, especially with the implementation of computer vision techniques in photogrammetry. These techniques are very comparable, but it will depend, of course, and it's also mentioned here, it will depend on the geometry of your feature, it will depend on the texture of your feature. Lack of texture, lack of ambient light will definitely won't allow you to make accurate photogrammetric results or any results at all with photogrammetry. So in that case, it's more a matter of suitability of a technique. To give you an idea of this, of the complexity of the scenes, I would like to show you a website that I found online. Where's my browser? Here's my browser. I think I have to go to this one. So this data is are acquired with a scanner, a 3D laser scanner, with a panoramic camera, with an integrated panoramic camera. It's called a Matterport scanner. So that scanner looks like this. And actually, the thing that you're looking at, if you know from the old days, the Microsoft Kinect, where you have an Xbox and you can connect your Kinect to the Xbox and you can have interaction with your device, like dancing and playing music and stuff like that. Actually, that system is implemented here in this type of laser scanner. So this is extremely useful for indoor environments, but definitely not for outdoor environments. But the idea here is that you have a rangefinder, a laser scanner that's rotating, that is simultaneously making panoramic pictures. And the result of that, of this very fast data acquisition technique is, I lost it again. Allez, I have too many tabs here. Yeah, voila. Is that here you have a look on the panoramic images, and you can just, in this environment, you can go from one side to another. By the way, I took the interior of a museum here in Luxembourg, I think. So this is the panoramic viewer. And if you go here, you actually have a 3D representation of the point cloud. And you can have full access on of your 3D environment, which is actually quite cool, especially for virtual visitors, rendering it quite interesting. Just to give you an idea, the scanner in this case will cost you a few €1,000, which is quite cheap compared to the scanners that are currently on the market. The thing that you will have to pay for in this case, except next to the scanner, is the processing of the data. So you will, while making scans, if I go back, I think I can refresh this one. If you go back to the initial viewer, you will see here multiple views of the scanner. So all these points here are just scanning positions. They have to be aligned, so they will have to be registered, and that's something that we will discuss in a few days. But this registration, this process of making your data spatially coherent is done on a cloud that is owned by this company, and you will actually pay per square meter for getting the data. So it's a pay by use system rather than just buying a laser scanner. And that's something that can be useful for your application or not useful for your application. That's something that you, of course, have to decide yourself with your project holders. But the results are quite impressive from my perspective. But we don't own a system like this in our institute because of the pay-per-go license that you have to apply for. But still, indoor-outdoor environments are can be modeled using laser scanning. So here another example of the St. Babs Abbey in Ghent, multiple laser scannings that are merged into one coherent point cloud, where you have full coverage, of a large coverage of your historical artifact. So the biggest advantage of laser scanning is that we can obtain a massive amount of data, both in terms of geometry. So we have our X, Y, Z coordinates and possibly accompanied with an intensity value or an RGB value. From these data, these point clouds, we can easily extract volumetric information. So there's frequently a frequent application when you're working on deformation measurements, for example. You make a scan on day 1, you make a scan on day 2, and it's very easy to extract volumes out of it expressed in square meters, for example. But that's also an advantage that holds for photogrammetric applications. Compared to photogrammetry, the acquisition of the data and the degree of automation of the data acquisition is very high. So fast and automated data acquisition is a very interesting advantage of laser scanning. And it also gives you a panoramic, at least for a terrestrial perspective, a panoramic view that can also be an advantage. The disadvantages of laser scanning is that the costs definitely compared to photogrammetry are relatively high. Like, you can start making 3D models using a cell phone. So 100, 200, 700 euros for a cell phone. Or camera, digital camera, also starting from 100 to 3,000 euros with several lenses. You can go very expensive with that in terms of photogrammetry, but I think if you really want to have the top of the bill, you're in 5,000 euros. But the normal camera that is suitable for, at least for most research applications, for 300 to 500 euros, you have a decent device to make your photos. Whereas if you want to buy a terrestrial laser scanner, I requested an invoice a few weeks ago, and the starting price starts from 20,000 euros for a very small laser scanner. And if you really want the high-end laser scanners for the long-range distances, like the 3,000-meter laser scanners or the very dense, very fast laser scanners, you should think about prices starting from 80,000 to 100,000 euros for only the scanner without maintenance or software. The portability and the size of the scanner itself is also a potential disadvantage. like I was just talking about or referring to the 20,000 laser scanner, that's the BLK from Leica. That one is very portable, 4 kilograms. But if you want to go to remote areas and you are having a conventional scanner in terms of an HDS or a Trimble, like a Trimble scanner or the C10 scanner that I used yesterday, you should think about several kilograms only for the scanner that goes in a box. The boxes are quite heavy and quite voluminous, so it's not easy to transport them on a plane or take them on your back and go in your very remote areas. The data processing, that's also very important to mention. Data processing is more challenging and more computational intensive compared to photogrammetric data processing. So you will work with massive point clouds, millions and millions and millions of points, and it can be a challenge to process these data, especially when you only limit yourself to manual data processing, and also data management is more challenging or can be more challenging. So the main idea here is that you will work with massive data sets that you have to store. Like for example, if I go to my file explorer and I take my project of yesterday, so I had 5 scans, and these 5 scans have a total volume of 4.25 gigabytes for only 4 scans, or let's say 100 million points. So imagine that I was doing the entire site, because I only covered a small portion of the site. It can increase heavily. So laser scanner, okay, we have a site, we have desirability to apply laser scanning in our case. Then the question is, okay, when is it a good idea to implement laser scanning? And many articles or many handbooks that deal with introductions on laser scanning, they will show you an illustration that looks like this one, and it will actually give you some kind of an impression or some kind of a rule of thumb to give you an idea on, okay, when should I use hand measurements, terrestrial topography, so conventional topographic total station measurements. When can I use terrestrial laser scanning or photogrammetry? When should I use GNSS, satellite remote sensing, airborne applications? And that actually depends on the object size on the one hand. That's what you see here on the x-axis. If my Agisoft is working with me. On the x-axis, you see an impression of the object size, and that goes from objects that have very limited dimensions, like 1 decimeter, to multiple hundreds, up to 1,000 kilometer dimensions of your study object, like entire countries. And most of the time, like for an archaeological site, for example, you will be somewhere around here. And small artifacts, tangible features like pottery is obviously somewhere here. The complexity, so this is about the desired complexity of the final geometry of your feature in terms of points per object. That's what you see here on the y-axis. So if you just have a small object and you want a single measurement, yeah, measure it by hand, or if it's a very large area, measure it using GPS. However, if you really want to have a very dense, representation, geometrical representation of your object, you should think about satellite remote sensing for large objects, airborne data scanning, airborne laser scanning, or airborne photogrammetry for mid-range objects. And then here in the middle, you find somewhere the transition from airborne to terrestrial laser scanning applications. So actually, if you say, okay, we have a large archaeological site and we want to cover it by laser scanning, it might be a good idea to think about the application of airborne laser scanning, which is of course much more expensive, but far less labor intensive in terms of data acquisition. But if you just want to cover a small portion of it, then you can think about terrestrial photogrammetry or terrestrial laser scanning. So that is how to read this illustration. Okay, we are using the visible light, so light that is generated by our sensor or by our scanner. And in that case, I would like to go into a little bit more detail about the meaning of light. What is light actually? So imagine the situation that we have a reality, a certain reality. And in this case, I found a Google 3D representation from Google Satellite of the campus of the Ghent University. So this is the department where the building where the geography department is hosted in Ghent. And if you make a visible light picture of that, we have here a visible camera, you can get a true color representation of that site. So imagine you're in a plane, you make a photograph of that area using a visible light sensor, like just a normal camera. You will have a digital image that corresponds with the vision that we would have if we would be in the plane ourselves and look down from our plane. That's what you would see. And also you see here a histogram of the different layers in your color that also correspond with the representation of that image. Of course, we can also obtain different wavelengths. So that's, for example, what you will get when you work with near-infrared imagery or infrared imagery. Of course, if you look around, you don't see the infrared or the near-infrared because the light is not, your eyes, your human eyes are normally not sensitive to near-infrared or infrared. But it is possible to capture the reflections of the objects and then actually make a record of the different degrees of near-infrared reflection. And by doing that and making composites of near-infrared, red and green layers, you can actually make these false color composites. What's actually happening here is that we are talking about the spectral, the electromagnetic spectrum of light. So, for example, the sun emits all visible of all the wavelengths in that spectrum, and then we're talking about several wavelengths. So, for example, radio waves, microwaves. These are very long wave signals. Whereas if you talk about gamma rays or X-rays, these are very short wavelength signals. And somewhere in the middle, somewhere here, there's a small portion of that electromagnetic spectrum that is that allows us to see our environment. So as you can see here, that's a very short portion of the spectrum that we are able to obtain. So it's actually here the visible spectrum. What we are doing when we're talking about laser scanning, most of the time, we will just take a small portion of this spectrum, the infrared spectrum, or in some cases also the visible spectrum, and we will emit a certain signal and capture the echo of that signal. But even more, we don't necessarily capture the reflection of that signal. We're actually using the time of flight, like I already said. We're using the time of flight to obtain the geometry. So it means that we get a representation of the geometry of our feature, but also already mentioned the intensity value that can be captured while working with laser scanner. And that's what you see here. So here you also see a representation of the geometry, the same representation as the representation that you see here on the left-hand side. But instead of visualizing the color as a function of the altimetry on the left side, here on the right side, you see the color as a function of the intensity of the signal. So what's happening here, we're sending 100% of the signal. Just to explain it very briefly here, we emit 100% of the signal. And in this case, on the roof of the building, we have an echo of 90%. Here on the floor, we also have an echo of 90%. Here on this area, the circular roof, we have an echo of 60%. And in the trees, we have an echo of 40%. And this difference in echoes or this difference in intensity values, because it's resulting in a difference in intensity of the reflected signal. That's also a very useful property that you can use for point cloud interpretation. We will use that property just later on. So laser scanning, let's go a little bit more into the geometry of laser scanning itself. Yeah, this is my last slide, and then I would propose to have a little break. So the thing that is happening, we have our sensor. So let's say that P here, this is P, that is the location of our sensor, that is the location of our laser scanner, and our sensor has a certain position, let's say XP, YP, and ZP. And we have an object that we want to measure using laser scanner, and we call that object R, and R has, in this case, unknown coordinates XR, YR, and ZR. So that's any reflecting object that we want to measure in this case. And then the biggest challenge is actually to derive the vector, the distance vector, or the vector sensulato between P and R that defines the spatial relation between P and R as a function of our entire coordinate reference system. So this here, O, is the origin of our coordinate reference system. And by measuring the distance and by measuring the orientation, the horizontal angle and the vertical angle of our vector related to our system, we can actually derive the coordinates of our object. So we measure a distance, we measure a horizontal angle, vertical angle for each point. So horizontal angles, vertical angles, and distances. That's something that you would also measure with a total station. And by doing that 100,000 times per second or 500,000 times per second, you are actually working with a laser scanner. So the conventional terrestrial laser scanners, most of the times, this P point, so the orientation or the position of our laser scanner, is actually the same as the origin of our system. So if I go back to my laser scanner that I used yesterday, so for example, this one, no, not this one. Yeah, this one. So this is my scanner. And in most cases, if you use a scanner like this, it initiates itself by saying, okay, I have here a vertical axis. So if you're familiar with a total station, you know that you have to level your total station, resulting in a certain vertical level that is pointing upwards in relation to the gravity of your site. And you have a horizontal plane, and in that horizontal plane you have an x-axis or an x0 direction, and you have perpendicular on that you have a y-axis. And from that starting position, so this is the origin of your initial coordinate reference system. From that origin, you will actually measure this certain horizontal angular increment and a vertical angular increment. You will measure your distances, and combined with that, you will have a local coordinate system, a local point cloud, where all the points are then converted to Cartesian coordinates. And that's actually what's happening here. If your sensor is not considered to be in the origin, or if you have multiple scans that all start from the origin and you want to make these scans coherently, spatially coherent, you actually have to do point cloud registration. So you will have to combine the different point clouds, or you should use a global navigation satellite system. So for example, in this case, if I have a GPS here attached, or GNSS to put it more general, attached to my laser scanner, I know the absolute coordinates somewhere in WGS 84 or UTM or the national Belgium national coordinate system. But in that case, I also need a system to have my orientation correct, because a GNSS only measures a point. And of course, I need an orientation as well. So I need a motion sensor or a gyroscope or a compass to set my orientation straight. So an INS or an IMU is more for kinematic applications, and a gyroscope or a compass is also applied for static applications. And then these angles, which is actually a registration of a rotating mirror for the vertical angles, and the registration of our horizontal angle, combined with the distance measurement, with the electromagnetic distance measurement, will result in the polar coordinates of our point, and these polar coordinates are then converted to Cartesian coordinates. And that's something that will be discussed in the next slides, how we can actually extract our distances using electromagnetic distance measurements. I don't know if you have any questions so far that you would like to share. But otherwise, I would like to propose to have a little break of, let's say, 10 minutes. That we meet again at 5:20 Central European time. Are there any questions? I hope you have not fallen asleep.
No, you're awake.
Don't speak so loud, you woke me up.
Okay, let's meet in 10 minutes then. I will pause the recording. Start the recording again. Voila. Share my screen. And go back to the presentation. So in this schema, you see distinction of the different techniques that can be used to extract distances or geometrical representations of features. And it's actually a combination of what we already saw. So we have light, environmental light, or just the electromagnetic spectrum of signals. And derived from that, we have passive data acquisition techniques. And one of these passive data acquisition techniques is photogrammetry. That's the thing that we discussed in the previous session. And also we have active data acquisition or an active geometrical representation where we can work with time delay, so time of flight, scanners that are frequently used in heritage documentation. And then we have pulse and continuous wave techniques that will be discussed later on. And another thing that we can apply when talking about active data acquisition is triangulation-based techniques, where we have line scanners, pattern projection, or single spots. During the break, I recovered the tutorial that I was working on many years ago while making my own laser scanner. It's actually this thing here: make your 3D scanner from a webcam, laser pointer, and free software. And the idea here is that you have, like I said, a pointer. You aim your pointer in a certain direction with some reference measurements. I will actually just put it in the chat function. It's quite an old thing. You see it here, 2011, but still it's quite nice to experiment with it. If I can access niet deze. Yeah, voila. Voila, so here you have the link if you feel like it. So let's talk a little bit more about the different ways of extracting distances using active data acquisition technique. These are the triangulation-based and the time of flight or the time delay techniques. The first thing that is most frequently used when speaking about laser scanning is the ranger finder or the time of flight time delay technique. And what's actually happening here is that we have the emission of a signal. So we have a laser driver, and the laser driver will emit a certain signal, and the backscatter of that signal is recorded, amplified, and using the time difference between the two, you can actually extract the distance between the sensor itself and the echo. So when topographers started working with the first topographic distance measurement devices, you will find something like this. These are the old-fashioned laser range finders. And actually the same technique is also implemented in these handheld distance measurement devices that you can buy in construction companies' shops. The basis of this concept and the basis also of laser scanning and the thing that I just showed you or shared with you in this URL is the fact that we are using laser, so light amplification by simulated emission of radiation. And laser is actually quite an old technique. It dates from 1958, and it uses or it's based on coherent light. So coherent light meaning that we have light in certain waves that are spatially and temporally coherent. If you look here, you have regular light. So we have a flashlight in this case, and the flashlight emits certain wavelengths in all directions, and the light is not coherent. So all the wavelengths intersects with each other. We have multiple waves in our signal. This is definitely not useful for the detection or the determination of distances, but we have to use coherent signals. And even more, we have to work with monogrammatic signals, meaning that we only need one wavelength in our signal. So we need filtered light, and even more, the combination of this filtered light and the coherent light will result in a coherent monochromatic signal that is actually laser. It can be a continuous wave or pulse. So we can send a signal, and that signal is spatially coherent and monogrammatic, and it's just a very short amount of energy that is emitted to our surface, reflected, and then analyzed. Or we can use a continuous wave that we emit, that we reflect, and that we will use for our wave-based distance measurement. These amounts of energy, and especially if we work with pulse-based laser scanners, these amounts of energy can be extremely high. And that is one of the reasons when you have, for example, a total station or a laser scanner, you will also always find a warning that you will definitely not, you cannot look with uncovered eyes into the laser itself, because it will harm your eyes. It can cause blindness and stuff like that. So definitely don't look in a laser scanner when it is operating, because of these high energy levels that are emitted. That's, for example, one of the reasons when I wanted to apply for an application for laser bathymetry. So laser bathymetry, like I said, the near-infrared signal is heavily absorbed by water. The green signal is penetrating, or can to a certain extent penetrate the water level, the water column. But in that case, you need very, very, very high energy levels. And one of the reasons why my application was not granted was because of the fact that these high level energy rates were applied on a beach. You will use laser scanner in this case on a very calm day. So when there's no or a very limited amount of turbidity in the water, but on these days, on perfect days, clear skies, no wind, etc., tourists will go to the beach. They will look up, and meanwhile I'm scanning with my scanner with my green signal, and that will definitely harm these people. So it was not granted because of safety reasons, and eventually they were totally right with that. The general idea about a time-of-flight scanner, like I said, we have a laser. The laser emits a certain signal, a signal that is spatially coherent. And from the moment that we emit our signal, we have an initiation of our timer. So we have T0, initialized time, T0. Then the signal goes with the speed of light to our object. We have a Lambertian reflection, and we have the echo of that signal that is again emitted or detected by the laser scanner. And then as soon as we reach our sensor again. We stop our timer at T1, and then based on the time differences, we can calculate the distance between the object and the sensor itself. And of course, if we implement that in a laser scanner, we have to loop that procedure until we have obtained our full coverage or the full area of our study area. So here, another way of doing that, in this case, the pulse-based scanner, a pulse, an emission, a reflection, detection, and then what's actually happening here, we have the start of our pulse, which you see here in this simple graph. We have the start of our pulse, we have the detection a certain amount of time later, and based on that time of flight, we can extract the distance using the speed of light. In the system that you see here, also with a simple graph, we don't emit a pulse, but we emit a continuous wave. And based on the phase shift of that continuous wave, we can actually find the distance between our sensor and the reflectant based on the phase shift. And this phase shift is of course related to the full wavelength of our signal. Since we are working with certain wavelengths, we can exactly know the full distance of a certain wavelength. So if we know the full wavelength and we know the portion of that wavelength, we can actually derive also the distance between our sensor and the reflectant. And that's the basis of phase difference ranging or continuous wave laser scanning. So these time of flight scanners or the pulse-based scanners, these are frequently used in airborne applications. So most of the airborne sensors that you will find online are equipped with these pulse-based scanners in the near-infrared or the infrared range of the spectrum. And also for many long-range terrestrial applications, like applications where you have ranges over the 1 kilometer, you will find these time-of-flight scanners, these pulse-based scanners, because of the fact that you can put a lot of energy in such a signal, so it can travel very long distances without losing too much of the energy on the way, because it has to go in one direction and it has to come back, and in that way it can lose a lot of energy, of course. So we need a signal to detect for our calculation of our distances. And that's why most of these long-range applications and airborne applications make use of these pulse-based scanners. And then the distance between the sensor, we call it P in one of our previous slides, and the object itself, object R, is then calculated by using the speed of light, so C, and the time of flight. So we have the speed of light, we multiply it with our time difference, the time of reflection and the time of reception, and we divide it by 2 because the signal goes in 2 directions. So we have to divide it by 2. And this T parameter, the time, is of course counted by the counter in the laser scanner itself, and it of course has a certain resolution, which will be very important in the next slide, or in 2 slides. For short-range terrestrial applications, like applications where the distances are limited to 80 meters, 100 meters, in many of these cases you will find continuous wave measurements, continuous wave distance measurements. And the big advantage of that is that these scanners, especially for these short ranges, have a very high speed and a very high accuracy. So conventionally, when you're working with a pulse scanner, you'll send a pulse, you will wait for the pulse, and then as soon as you have received the pulse, you can only then you can emit your next pulse. So you really have to wait for every pulse to be emitted and then come back. Of course, this goes very fast because we're working here with the speed of light. But in case of this continuous wave, we don't have to wait for the reception of our signal and then emit our next continuous wave, because we are continuously sending our signal. And that's a very big advantage that we have there. The only problem is that these waves do not allow us to put very high levels of energy on, modulate large amount of energy on this wave. And then instead of calculating the distance based on an explicitly measured time, we're using the phase shift. So this parameter here is the phase shift with the frequency and the wavelength of our signal. And using that equation, you can derive the distance from the sensor to the reflector. The full number of waves are not included in this equation. So if the wavelength is significantly or is larger than the distance of I'm mistaken here. If your the number of wavelengths is more than 1, so in this case, for this equation, we measure a fraction of our wavelength. But of course, if you have covered multiple wavelengths in your distance measurements, you can of course not derive the distance anymore, and that's why many of these systems make use of dual wavelength systems, where you have a long wavelength to calculate with a lesser accuracy the distance. So it gives you an estimate of the distance, and then this estimate of the distance is then fine-tuned by the portion of the short wavelength estimation or calculation. So here an overview of the two range equations that you see here. So here for the time of flight or the pulse-based laser scanner, the range, and here the range for the continuous wave estimation. So the phase shift in the lower figure, in the lower graph, and the pulse-based on the upper graph. Like I said, the resolution, so the temporal resolution, and in that case also the accuracy that you can obtain with such a system is heavily depending on the resolution of your time. Hello? Is everything okay? Wait, there was a question. Yeah, indeed. C in the equation is the speed of light. The speed of light. So this is the resolution, and in this case, the resolution is defined by the wavelength of half the wavelength of the long-term wavelength. No, sorry, the short wavelength portion that can be measured on the fraction of the distance interval. More recent laser scanners. More recent laser scanners like the Leica P40 or the P50, and there are many other laser scanners that implement this system nowadays. They combine the two advantages of both types of laser scanning, so both the pulse-based laser scanners and the continuous waveform laser scanner. These are much more accurate because you can really measure on the wavelength itself, whereas these types of laser scanner, like I said, they have a very long, they have the possibility to measure over very long distances. If you combine both advantages, you will have a waveform digitizer, as this is called by Leica, where the continuous wave is actually modulated on the pulse that is emitted. So every pulse is not only just a binary pulse or an amount of energy, but in that amount of energy, there's actually some kind of a timestamping available. And when you send a pulse with that timestamp in your distances, you don't have to wait for the previous pulse to be received before you can send the next pulse. So it's actually a combination of both. So you will have very long range laser scanners, but also with the same accuracies as you would have with continuous wave laser scanners. So for your information, that's at the moment the state of the art. Then a few words about the laser scanning triangulation system. And in that case, we were talking about the projection of points, lines, and patterns. The main idea here is that we have a source, a data source, an energy source. We have our receptor, or the place where we receive our echo, and the base between these two, so the distance between our emitter and our receiver, that baseline, that distance is known and fixed during the acquisition. And then by moving the sensor and the receiver over your object under different angles, you're actually able to make a 3D representation of your object by measuring the deformations of your emitted signal, a point, a line, of a pattern on the object. If, for example, you have here a pattern in emission, a receiver, if you move that upwards, downwards, to the left, to the right, the projection of that pattern will be received differently, while the object itself stays stationary. So that's very important also to mention here that we're working with stationary objects. If the object stays stationary and our pattern changes, it means that our orientation has changed, and based on the pattern itself, or based on the orientation of our point, or the location of the projection of your line, or the orientation of your point, the location of your point, you can actually derive the geometry of your object. And that's also what is explained here. So we have our laser and we have our camera. So the camera is just recording the signal. We have a base situation where we have a certain angle, a reference angle B, and a baseline that is also solid. And then after initialization, you can actually move your object on the move your sensor over the object and extract your 3D information from this object. And in this case, the quality will heavily depend, of course, on the baseline, on the focal length, and on the distance of the object itself. So this is actually very similar to what you have with 3D photogrammetry or image-based 3D modeling. But in case of working with environmental light, you're fixing your light and force your sensor to let it come from a solid or a fixed orientation related to your camera. Here are some examples of these kinds of triangulation sensors. So here you have the camera itself, you have the projector, and then based on the orientation or the reception of this signal by the sensor, you're actually deriving the distance, and by rotating and moving your sensor over the object or in relation to the object, you are able to extract 3D information out of it. These sensors are very useful for very short range applications. So applications of objects or measurements of objects that are relatively small compared to the conventional or classical laser scanning applications. So for example, when you really find where you find these types of scanners is for prototyping. So especially in the automobile industry, for prototyping applications, reversed engineering applications, where you have an object and you really want to have a sub-millimeter accurate representation of that object to make a replica of that object. But of course also for artifact modeling, this is a very useful technique. But these scanners are definitely not cheap. Accurate, but not very cheap. And then of course, what I also sent you via the URL, just your own line scanners or split scanners, where you have a pattern projected on your artifact, and the artifact itself, or the projection of that line on the artifact in relation to a reference pattern on the background will allow you to make a 3D representation. So very nice if you want to give it a try. Yeah, and of course this can also be used not only for by laser light, but also if you just have a pattern projection. So even if you have a beamer and you use the beamer, the projector, and you project a certain line pattern on your objects, you can use that object for geometric reconstructions because of the change of the patterns in relation to the equidistance of your black and white lines in this case. So system classification, so far we have talked about spaceborne, very limited about spaceborne, but mainly about airborne and terrestrial. Very interesting to tell you here is that airborne laser scanning are already referred to airplanes where you have a laser scanner mounted and where you fly with your helicopter or your airplane over your study area. But it is also possible to implement your or integrate your laser scanner with drones. Of course, the most lightweight drones still have a mass of 1 kilogram or 1 kilogram and a half or 2 kilograms. So your drone needs to be a high performance drone, of course, or high performance UAV. And of course, if you take a do-it-yourself drone for a few €100, you will definitely not put a 40,000 euro laser scanner under it. So most of the times, if you want to implement laser scanning with unmanned airborne data acquisition, these packages are sold as one service. Like Regal has it's called the Baticopter or the UAV copter, where you have a laser scanner and a drone integrated into one system where all the all the hardware is aligned correctly. For terrestrial applications, I already mentioned very briefly the kinematic applications, mobile applications. For example, what you see here in the lower part of this slide is the Regal Regal system, but also Leica has a system like this, the Pegasus, where you have multiple laser scanners mounted in a racket system. And integrated in that system, you also have a motion sensor, a GPS. And if you move your platform on your site, it's actually capturing a lot of profiles, 3D profiles that are then integrated into one massive point cloud. And static laser scanning, the close range laser scanners, most of the time these are the triangulation-based laser scanners, and then the medium and the long range laser scanners. So for terrestrial laser scanners, this is an example of a screenshot of the scanners that we have in our department. These are the scanners that are most frequently used or conventionally used also in archaeological sites for the documentation of architectural artifacts. And these systems are fixed on a certain position. So you have a tripod, and on the tripod you mount your laser scanner. And the fact that we have this laser scanner in a fixed position also allows you to obtain the highest accuracy that you can get with systems like this. So kinematic data acquisition always has a lower accuracy compared to kinematic acquisition always has a lower accuracy compared to static data acquisition because of the fact that we are static and we don't have to measure our orientation and positioning of the sensor itself. If we look a little bit more closer to this terrestrial laser scanner, what we actually see is that we have our vertical axis. So that is actually the same as what you will have with a total station. You set up your total station and make sure that the vertical axis is nicely aligned with your gravity. And then in that or on that vertical axis, we have a mirror, a rotating mirror that will define the vertical angles, and we have a vertical rotation that will define the horizontal angle. So we will rotate around our vertical axis, allowing us to measure the horizontal axis, and the mirror, the rotating mirror, will allow us to measure or record the vertical angles. So mobile terrestrial laser scanning is possible, but it is more expensive and more complicated and less accurate than static laser scanning. So it means that we have a dynamic system with a laser scanner on board of a mobile platform, like Mobile Mapper or in an airborne application. But in this case, since we are not in a static environment, but in a kinematic environment, we need to record our motion using a positioning and orientation system. So POS here stands for positioning and orientation system. And the P component, the positioning, is managed by the global navigation satellite system like GPS or Baidu or Galileo. And the orientation is managed by a motion sensor, ENS, or several IMUs. And this will result in medium precision or medium to high precision, medium precision and medium to high resolution point cloud of your environment. The big advantage of this system, of course, is that you can cover much larger areas or larger sites when you compare it to terrestrial laser scanning, speaking in terms of time, of course, time and manpower. Here, an application of the Department of Geography of the Ghent University. This was a system that we built for beach, or that has been built for beach monitoring. So the topography of sandy beaches, where we had an amphibious vehicle. And here you see the laser scanner mounted next to the laser scanner. You see a motion sensor, 2 GPS antennas. And these are all aligned, all calibrated, because you need to know where your GPS is, where your laser scanner is, where your motion sensor is. This all needs to be in a rugged system where all the internal orientation and the interior planimetric and altimetric and angular offsets need to be known. And also timing is in this case very important. If you do a measurement with a speed of 500,000 points per second using your laser scanner, then you need to know while moving which point has been taken when and where. And in order to do that, you need, of course, a time stamping of your GPS and the time stamping of your motion sensor, which are obviously not measuring data with the same speed as a laser scanner. And then a little note on airborne laser scanning data, or airborne laser scanning data acquisition. By the way, we will work with airborne laser scan data very soon, in one of the coming days, and I will also already show you one of the examples of what we will be, the data that we will be using. And airborne laser scan data is very useful to cover large areas and to measure topographic surfaces in 2.5D or 3D. Fast and relatively accurate. Not as accurate as terrestrial kinematic data acquisition, and definitely not as accurate and dense as static terrestrial laser scanning. But the biggest advantage here is that we can really cover large areas. And if you compare airborne laser scanning data with techniques like photogrammetry, with photogrammetry, we know that what you see is what you get. So if you're flying over a topographic surface, you will measure this topographic surface. But if you're flying over a forest, you will actually measure the canopy of that forest. The big advantage of laser scanning in that case is that the laser will penetrate also the canopy of your forest. So you will have the top layer of your canopy, but you will also have layers in the tree mass itself and the topographic surface under the trees. So actually, by using airborne laser scan data, you will be able to get the topography of the area that is normally covered by canopy. In this case, it is also very important, especially given the high speed of the platform, to have a positioning and orientation system. And these also needs to be calibrated for internal system calibration. So the time latency parameter, lever arm, so the positional offsets, and the bore side calibration, which are the angular offsets. If you're measuring with your scanner like this and your motion sensor is here, or your motion sensor is positioned like this, that you know about these angles related to the laser scanner and that everything is aligned correctly. This is a very good moment to show you one of the, or to show you the airborne laser scan data that you will be working with in Cloud Compare. So I obtained a freely available data set from the Flemish government. So this is an area that is situated at the, it's called the Campina Plateau near the Meuse Valley in the Flemish region. And why did I take this area? Because it looks just like a forested area. You see the different trees. We zoom in or make the points a little bit thicker. take a shader. You see the different trees. You see some vegetation on the surface, on the topography. This is actually I don't know the heide. Yeah, doesn't matter. But why is it so incredibly interesting to work with these kinds of data? Is that after classifying the data, so after saying, okay, this point is belonging to a tree and this point is belonging to the topography of our surface, you can actually make a distinction between ground points and non-ground points. And if you then filter, this is, by the way, something that I will show you in more detail in one of the coming demos. If you then filter out all the non-ground points, and we go back, then what you see here, I make my points a little bigger, is that here in this area, there are some very strange artifacts that initially we didn't see because they were covered by canopy. By eliminating all our trees and only taking into account the points that belong to the topography, you can actually see some underlying microtopography. And what it appears here is that this area is of very high historical value, because this was the area where the German soldiers, before they were sent to the Western Front in Ypres during the First World War, in this area they were sent for training. So the Germans made trenches here. They have some foxholes. You also see here the craters that were made by shells, bomb shells. And you can just see it in the current topography using laser scan data and using some very simple topography enhancement techniques. So that's the potential of airborne laser scan data. And you can do that for the Flemish, entire Flemish region, or the entire region that you have covered using airborne laser scan data. I will skip this. Yeah, this too. So let's talk about, and let's finish a little bit about the deliverables. If you have your point clouds, and this is illustrated here by airborne laser scan data, but it actually holds for all types of laser scan data, also terrestrial data that we will work with. Laser scanning will allow you to, of course, generate a geometrical representation of your feature of interest, but it will also allow you to work with additional parameters like the intensity value. If you combine the laser scan data with color information, you will have photorealistic point clouds like the one that I generated, of the site here in my municipality. And if you have that point cloud and you apply some feature detection techniques on it, you can also work on point cloud classification. So say, okay, this point is a topographic point, we have building points, we have vegetation points, and you can define several classes and apply them, in this case, on airborne laser scan data. Of course, if you have your point clouds, you need some additional tools also to enhance visualization. In this case, I applied a shader on an airborne laser scan point cloud. But if you don't use your shader, you just see a series of 0D points somewhere in a 3D space. So it's just a massive point cloud. You cannot interpret it very easily. And that's why we have to discuss also about point cloud visualization, playing with the size of a point. Of course, a point, like I said, is a 0D object. But if you give that 0D object a certain dimension, a size, you make it a sphere or a splat, you can distinct one point from another, and you can actually use the relation between different points to actually do some kind of a point cloud interpretation. You can work with point shaders, and that's something that we will experiment with in Cloud Compare. And then about the deliverables, so the point products. For your own information or for data management, the point density measures are very interesting. So it gives you an idea of the coverage of your data. We didn't explicitly cover that in the photogrammetry part, but definitely here it's very important to use point density because it will allow you also to define the resolution, the feasible resolution of your digital elevation map. It will tell you something about the distribution of your points. And of course, we also have to consider here the different topographic parameters and the distance between the platform and the object itself. And then if we have our point cloud and we have our colored point cloud because of the combination of photogrammetry and laser scanning, and then it becomes very interesting. So digital imagery for the point cloud coloring, the geometrical representation derived from LiDAR, derived from laser scanning, and absolute georeferencing using the combination of GNSS and motion sensoring. Then you can actually derive a lot of information like digital surface models, terrain models, orthophotos, in false color composites, true color composites. So actually, in many applications, you will find a combination of photogrammetry and laser scanning and absolute positioning for multiple applications. Imagine that you will have to order a plane for deriving a point cloud of an area. In that case, it's relatively cheap to combine your laser scanner with a camera because most of the cost will go in the startup costs to take off and land and fueling of the plane. So if you're in the air already, why not take a camera and acquire some more data? It will also allow you to derive a lot of additional deliverables. And also the combination, this is actually something that I already showed you. If you have the combination of not only the geometry, but also the true color composites, it will allow you to do topographic enhancement techniques, and especially in combination with crop mark detection. So the techniques that we discussed with photogrammetry, crop mark detection, combined with topographic enhancement techniques, is very useful for the detection of underground archaeological features or paleo channels or something like that. The combination of terrestrial laser scanning and terrestrial photogrammetry allows you to generate these photorealistic points. And in most laser scanners nowadays, the camera is integrated in the scanner itself. So it will give you the option to not only capture geometry, but also capture the photorealistic geometry. And in most of the point clouds that I will show you and give you for the demos, there you will find a color code assigned to each and every point. It will allow you to improve the interpretation of these points. But of course, point clouds or making point clouds is one thing. You can put them on the internet using these JavaScript-based renders or some commercial renders. But you can also use the point clouds to extract more advanced deliverables like cross sections, plans, orthophotos, digital elevation models, of course. And we will work on these kinds of applications. Like for example, if you have an irregular point cloud, you can make some sampling of it. We can interpolate these data in order to derive digital elevation models, digital surface models. If you have a filter for the distinction between terrain points and non-terrain points, you can derive digital terrain models from these data. So it's an extremely useful data source, especially when we're talking about airborne laser scan data. Yeah, and this is a lot of text just to summarize everything that I just said. So the advantage of points, we won't lose any information. We have our raw data. We can use point splatting or point volumes, point radii to increase the readability. But it's very difficult still to extract information out of these point clouds, to interpret these data. So in most cases, we will work with surfaces that are derived by interpolation for DEM extraction, or by 3D meshing, 2.5D meshing or 3D meshing. And these meshes can then be used in additional information or in additional software for further processing, like CAD, GIS, BIM based applications. But of course, this also involves some data losses. Most of the time, you will lose some resolution, or you will lose in resolution because of filtering, because of resampling, or the interpolation in general. So some final notes to close it. Yeah, we need these point clouds for a very accurate, very dense representation of our artifact of interest. It will allow us to extract these data very fast, but we will also need to put some additional effort, or much additional effort in the data processing, data management. So instead of being on site for a very long time, because of the fact that we have to take our photos, and photo acquisition can be quite time consuming, especially for very complex sites. If you want to have a full coverage, you need a lot of photos. If you have a laser scanner, the same data can be acquired in just a matter of hours or days. So it will save you time and money on site. But of course, if you go back on site to the office, you will need more time for data processing. So yeah, that's what I wanted to say about laser scanning. This is the end of my presentation. Tomorrow we will talk about data management. So we will assume that we have been on site, we have acquired our data, and then tomorrow I would like to go a little bit deeper on how to deal with these data, how to manage these data, and just a little bit more also about the different deliverables. I don't know if you have any questions about this first session on laser scanning. In that case, I would like to welcome you for the tomorrow session on data acquisition, unless you're interested in what I did here, because I promised you to explain a little bit about the 3D modeling of this box. So what I did, I just put the box here on my table. I took my cell phone and I acquired pictures. I didn't make a full coverage of the object itself, but just of the front side. So I made sure that I was focusing on the object itself, and then I rotated. Let me zoom out a little bit to give you a better impression. I rotated around my object, and I made my photos like this. So if I align my photos, I think there's also a dense point cloud here. Voila, then this is the object that I have so far. Well, the promise of the problem that I experience here is that I don't have a laser scanner with me. Also wouldn't be that useful for just such a simple object. But instead of using a total station, I take my ruler. Let me go to my, can I show my camera that I'm definitely sure that you are able to see me? I hope it's visible. But what I have here, I have my ruler and I say, okay, I have a distance from this point to this point. Let's say that that is 14 centimeters. So I will write down for a box, I will make a sketch of a box. Let me make a sketch of a box here. And I say that this distance here is 14 centimeters. So this 14 centimeters actually correspond with this distance that I have here on the top. Then for this distance, so from here to here, I measure a distance of, let's say 4.7 centimeters. So 4.7 centimeters. And for the height of the box, so from here to here, I measure a distance equal to 19.5 centimeters. So what I will do now, I already assigned 4 points. Let me take this photo. I already assigned 4 points to the corners of the box. Of course, this is not absolutely accurate. Maybe even in relation to the absolute dimensions of the box, it's far from accurate, but still it gives me something. What I will do now is say, okay, this is my the origin of my coordinate reference system. So I will say that point 1 has coordinates 0, 0, 0. Then point 2 is actually the z-axis of my coordinate system, and I wrote down that the distance from point 1 to point 2 is 19 centimeters. So either I can say, okay, the distance from here to here, I select my 2 points, right click, add scale bar, and I can say 19 centimeters. But in this case, I will just say that my x coordinate here is 0, my y coordinate is 0, and my z coordinate is 0.195. And this is my z-axis. The point 3 in this case is situated on my x-axis. My x dimension was 14 centimeter. So here I will enable this marker. Oh, will not enable my marker. I will say this is 14 centimeters. It is on my 0. My y-axis is 0, and my z is also 0. And point 4, last but not least, it has a z value of 19.5 centimeters, and it is a y value of 4 centimeters, and the x is equal to 0 in this case. And if I align, or if I update my my system, I will see here that it has not been acquired very accurately, my points, but I have an error for the points that I obtained here of 1 millimeter. And in that case, I defined my own coordinate reference system using a ruler. There was a question. Can I suggest a portable laser scanner in 3D? Oh, something to attach to your phone. I just saw on the website of Matterport. If you go to this website, I will share it with you. Voila. That apparently there is a system available where you can use a laser scanner on a smartphone. However, first of all, I have no experience with these kinds of systems, but I assume that this is, if it is using some kind of, in addition to your phone, that it's only suitable for indoor environments. So maybe it can be used for museum applications or for real estate applications, but I would not recommend to use it for artifact modeling, and definitely not for outdoor uses, because the amounts of energy that you can emit with these kinds of devices is of course quite low. And I'm not sure how it works with the alignment and the registration of these data. So that's definitely something that you have to look at. But apparently you can start for free, so maybe interesting just to give it a try. Fortunately, I don't have an iPhone. If I remember.
Okay, thank you.
Yep, but I'm not finished yet. I'm not finished yet.
I'm sorry.
DPI, it's not DPI. Handheld scanner, 3D. There are also scanners like this one, for example. Sense RS, so apparently 600 euros. This is also for indoor object scanning that you can use. These are relatively low cost. I was actually looking for I think this one. Let me see. No. Yeah, these are all,
Because in Brazil, this kind of stuff is so much expensive. So I was thinking about to buy it low cost 3D scanner.
Hmm?
So I think the 3D systems is I think this one is okay. That
For what kind of applications would you like to use it?
for buildings, external and internal.
I would definitely not recommend this for building modeling.
Mm,
Definitely not. You will be disappointed.
okay.
We just, or we at my institute, we are in the process of buying this, but it's of course another. This is a low cost terrestrial scanner,
Okay.
like a BLK.
Oh, Leica.
Yeah, and then you're in the range of at least for an institute. I think it was 70,000 euros.
It's okay. Okay,
So,
Professor, thank you for your service.
You're welcome. But just please keep in mind that these systems that I just showed you, they are very useful and interesting for short range applications, indoor, but definitely not for outdoor applications.